Hello, everybody, and welcome back to Learn About Science. Today's topic, we are going to learn about the science of work. So, we're going to learn about what work means from a science perspective. So, it's not like working on your assignments. This will be an actual physical meaning for what work is, and we'll quantify it today and we'll explain what it means. Okay, so today's basic objectives are to number one, calculate work given an applied force and a distance traveled. Of course, we'll define what work is first. Number two, identify the units for work. So, like centimeters is a unit of measure for lengths, and a gram is a unit of measure for weight. We will talk about what the units are for work. And then lastly, today we'll talk about calculating the efficiency of a machine given its input and output work. This will be similar to the efficiency calculations that you did the last day in order to figure out the efficiency of a machine by looking at its mechanical advantage and its speed ratio. The calculations will be based today on input and output work, and so it's just another way to calculate efficiency, or another way to calculate how much energy is lost due to frictional forces. All right, so let's start things off here with what is work? What is the meaning of work? And in science, work is done when a force acts on an object to make that object move. And it's very important to make note here that the force that's being applied and the direction the object moves must be in the same direction. So if for some reason I was pushing on a big tire, and even though I was pushing it to go away from me, the tire was rolling towards me, I would not be the reason for the work being done on that tire. One would make an argument maybe if that tire was rolling down the hill, that the force of gravity was doing the work on moving the tire down the hill. But I would not be responsible for doing the work, as the force I would be applying and the direction that the tire moving are not in the same direction. So that'll be one thing that I'll stress over and over today, that work is only done when a force acts on an object to make that object move in the same direction. And of course, movement is needed before you can say that work has been done. So let's give another example here. I'm pushing on a wall. While I'm pushing on the wall, I may be exerting some energy, but I'm not doing work unless I get that wall to fall over. And then one can make an argument that I did work. But if I'm pushing on a wall and the wall does not move, there is no work being done. Okay, so a lot of the reason we talk about work is there's a lot of calculations that will be done starting this year and moving forward into high school, where you're going to be calculating work, and it'll come into play for analyzing a lot of different situations. And for what we're looking for this year is to calculate work input and work output so that we can do an efficiency calculation for a machine. But before we get to that, we need to learn how to calculate work. And work is simply force multiplied by distance. So we'll take the force in newtons that we've been talking about here, and we'll multiply that by a distance. And the distance that the unit we'll be using for distance will be in meters. So you can have different units for distance, but we'll typically do most of our calculations such that we will get units in newtons meters. Okay, so if you can see, yeah, it just cleared up there. Newton meters down at the bottom of the slide there. The units, or one set of units for work, is a newton meter, and that's because we will get newtons from the force, and we'll get meters from the distance. So multiplying them together, we'll get newton meters. Okay, so F is the force, D is the distance, and of course, forces will be measured in newtons, and distance will be measured in meters. Okay, moving on. The amount of work done obviously depends on two things, and we've already stated they are what showed up in the calculation. The amount of force exerted on the object and the distance that the object moved in the direction of the applied force. So again, the direction of the force and the direction of the motion of the object must be in the same direction. Okay, so an example here. If you lifted your chair onto your desk, how much work would you do? Well, assume that you have to exert a force of 50 newtons to lift the chair, and your desk is 0.4 meters high, so around 40 centimeters high. Well, we take our formula, work equals force multiplied by distance, and we'd substitute in 50 newtons for force, and we'd substitute in 0.4 meters for the distance, the height in this case. And 50 multiplied by decimal or 0.4 is equal to 20, and the units on that would be the Newton meters. Okay, and then we'll mention it right now. Another unit that we can use for work instead of the Newton meters is a Newton meter is also called a joule. And this was named after English scientist James Joule, who did lots of work with work as well. So I used work in two different ways there. Okay, so the relationship between energy and work. Energy and work are very closely related. Without energy, there could be no work done. Um, if you go back to a definition, energy is by definition, or a definition, is the ability to do work. So, energy is the ability to do work. It's expressed in joules. And work is the expression of that energy being used to do something. Okay, so the way to kind of get this in your head is an example here. When you ride your bicycle, you exert a force on the pedals. The chain transfers that force to the wheels, causing them to move. Your energy is used to provide the force. So the energy in our body, in our muscles, is being used to provide the force that drives the pedals that moves the wheel. Work is being done because the force that we apply to the pedals causes the bicycle to move. Now, with gears, we do have a different direction that the gear is being moved downwards, obviously, in the case of the lever of the pedals attached here. But when we look at all the transfers of direction due to the gears and the chain linkage, we ultimately will get the force is actually going in the same direction as the movement of the bicycle. That would be the challenge on that one, is understanding that the force and the movement are actually in the same direction. But that is because gears have the ability to change direction as well. All right. Another example to look at here is a vehicle. So the plain old gasoline engine in most of the vehicles that you guys would be driving, or not driving yourselves, I suppose, but your parents would be driving, and that comes from gasoline in the tank. So the energy source in a vehicle is the gasoline. The combustion of the gasoline in the engine provides the force that makes the work or the car moving possible. So the machine transfers energy from the energy source, the gasoline, to the actual tires, causing them to rotate. And earlier you learned that machines help us to do work, and they do that because they help us do work by transferring energy. One thing you're going to learn is that when we use machines, it's not that we do less work. The same amount of work will need to be done. But going back to previous lessons, you know that using a machine either gives you a force advantage or a speed advantage. Okay, and so that's what you need to think about. In terms of energy, you'll find out, because you've done efficiency calculations, that we always lose energy due to the frictional forces. So there's never going to be a 100% efficient machine out there. It's theoretically impossible, because there is going to be somewhat of a frictional force, okay, for a machine. I do not know of any experimentation that's been done without any frictional forces. I'm sure they experiment on that to this day, but as far as I'm aware, nothing has been successful on that front. Okay. The next video here is it's a nice little video I found on YouTube. It links energy, force, and work. I'd ask that you guys watch this video. They go a little bit more depth, but I would say watch from the beginning to the first 3 minutes of the video, and that's perfectly fine for our objectives here today. But feel free for anybody who kind of wants a glimpse into the future, what you'll be doing in upper levels of junior high and going into high school. That's kind of where the video takes you. Kind of goes into grade 10, grade 11 science, physics a little bit there. All right. So back to work and machines. Using machine does not mean that less work is done, but you use the machine so you do not have to exert as much force, but you still do the same amount of work. So typically it's for force advantage, but like we talked about with the bicycle, sometimes you actually want a speed advantage. So it's either a force advantage or a speed advantage. So to put this in perspective, we're going to look at a scenario here. We're going to prove that work is the same whether you use a machine or whether you do this job without a machine. So we're going to take a look in the context of an inclined plane. We're going to talk about how much work is done by pushing this student on the wheelchair up the inclined plane, or if we were to just lift the student up directly the distance that they gained in height from using the inclined plane. Okay, so let's start this off. A pushing student exerts a force of 320 newtons for a distance of 5 meters. So they're pushing on the wheelchair, 320 newtons, a distance, so this total distance here, of 5 meters. This comes down to doing our calculations. So work input in this case is the input force, which would be the force that the young lady here, it looks like, is pushing with, which is 320 newtons. And the input distance here, so the distance that's being traveled with that force, is 5 meters. So 320 newtons multiplied by 5 meters would give you 1,600 Newton meters, or as you can already see here, that would be the equivalent to a joule. So 1,600 joules is the same thing as 1,600 Newton meters. Either units are acceptable. Okay, so now comes the next side of this. How much work would be required to lift that person up to the top of the ramp without using the inclined plane, like just basically lifting them straight up and onto the upper level. So let's take a look at that. So the machine has lifted the student in the wheelchair up 2 meters. So this distance up here, they actually moved 5 meters, but the ultimate height advantage here is 2 meters. They've gained 2 meters. The downward force exerted by the student in a wheelchair is 800 newtons. This would be the force due to gravity. And so now we use our work formula to calculate this. So the work output in this case is the force output. So that's overcoming the 800 newtons of gravitational force. And the output distance would in this case be the 2 meters. So putting that into our formula, 800 newtons multiplied by 2 meters would give us 1,600 joules. Notice that this is the same value as the last calculation. So no matter what, whether we push the student up the inclined plane or lift them up to the platform above, it is the same amount of work. What's the difference? Well, the difference is that we only needed to use 320 newtons of pushing force to get the student in the wheelchair up the ramp. Whereas if we were to lift them straight up, you'd have to apply 800 newtons of force. Okay, and I just summarized that there, yeah. So both the work input and the work output equal 1,600 joules. The pushing student had to exert a force of only 320 newtons to move to a height of 2 meters. Now make note, they used this 320 newtons of force, but actually moved the wheelchair 5 meters, but only gained a height of 2 meters. So it was 320 newtons times 5, whereas without the ramp, it would have taken 800 newtons to get that height of 2 meters. Okay, so that is why they equal 1,600 joules. Okay, just a little fun little graphic here for you to see the same kind of scenario here. We've got a cart, and a cart is going up a ramp that's set to different angles. And of course, you probably appreciate here that the steeper the cart has to climb, the more that the cart has to overcome direct gravity, if you will. So in the in the first example here, in order to push that cart up, you only have to exert 9.8 newtons of force. However, you have to push that cart up a displacement of zero point 0.9 meters in order to get it to the same height over here. Whereas in the 45-degree angle here, we have to exert a 13.9 newtons. You have to push the the car has to be pushed a little bit less. I think we'll just take a quick look here. 0.636 meters is its total displacement to get to the same height. Okay. And then here, it's the steepest angle. You have to do more force, but you only have to push it a total distance of 0.52 meters. So where it all comes down to is at the bottom here with those calculations, force times distance, force times distance, force times distance, they all give you the same value of 8.82 joules. So in all scenarios, the amount of work is the same, but you use the least amount of force in the first scenario, and you have to use the most amount of force in the third scenario. And the most force that you'd ever have to apply in this situation is if the ramp was straight up and down, such that you were lifting it straight up. That would be the maximum amount of force that you'd have to apply. All right. So we know from a previous lesson that when we do work, there's always frictional forces that resist that motion. So when you do any kind of, or when a machine does any type of work, there is always going to be an inefficiency in it. And this is because the amount of work that will be put into the machine will always be more than the amount of work that is put out by the machine. And that's because the friction reduces the amount of work output. So if I were to put 100 joules worth of energy into cranking a pencil sharpener on the crank, on the other side, the part that's sharpening the pencil, there would be less than 100 joules of work being used to sharpen the pencil because there would be energy lost with the heat that's being generated and the actual breaking up of the pencil lead and the wood from the pencil itself. So that would be lost as energy. And if you've ever used a pencil sharpener, you can hear that there's loss of sound energy as well. So it's not going to be a huge amount in a pencil sharpener, but it either way or regardless, it would be less than 100% efficient. In this sample calculation down here, just so you can see, efficiency is calculated as the output work divided by the input work multiplied by 100. So with these numbers here, if you were to do 1600 joules worth of work and only got 1200 joules worth of work out of it, then you take 1200 divided by 1600, multiply by 100, and you would get 75%. Okay, 75% means that you're using 75% of the energy for actual useful purposes. The other 25% is lost due to frictional forces. All right, so to wrap things up today, calculating work given an applied force and a distance traveled. You'll need to know that the work formula is work equals force multiplied by distance. The force needs to be measured in newtons, and the distance should be in meters. There's the odd time that you could have it in centimeters. But for the most part, it'll be newtons multiplied by meters. You should also recognize that the units of work are newton meters or joules. You'll be expected to know that the units for work are newton meters and or joules. And then thirdly, from today, you should be able to calculate the efficiency of a machine given its input and output work. And the only complication to that might be that you might have to use your work formula to calculate the input work, and you might also have to calculate the output work. And then you put those solutions into your efficiency calculation to figure out the efficiency of the machine that you're studying. I hope you guys have had a good day today and that you understand what I'm talking about. If not, please feel free to contact me via email or join the Zoom meetings in the morning. Have a great day.